Professor Floyd here, and this is OEH 5723, homework set 7, problem number 5. And in this problem we have toluene evaporating from a dip tank at a known rate of 250 milliliters per hour. And it's evaporating into a room that is 47 by 30 by 10. So our generation rate is 250 mils per hour, and our room volume is 37. I don't think I said that right. It is 47 by 30 by 10 feet. So this equals. And so, anyways, getting onto the whole picture. There's no local exhaust ventilation to capture the toluene from the dip tank, but there's decent general dilution ventilation in the form of a shop fan that moves 1,000 cubic feet per minute out of the shop. And then inside the shop, there's good pedestal fans that create good mixing. So we're going to assume that this is a well-mixed environment. Is that reasonable for a real plant? Probably not. In this case, we're assuming that it's reasonable enough so that we can have a well-mixed box here. So our room volume in cubic feet is 30 times 47 times 10. So that's 14,100 cubic feet. And let's just go ahead and convert that to cubic meters, because in the end what I'm going to ask you is what is the concentration if this dip tank is covered up overnight and then in the morning it's opened up. 30 minutes after this tank has been opened up and exposed and it's emitting at 250 mils per hour, then what's the concentration of toluene going to be in that well-mixed shop after 30 minutes of having this tank open? So first, let's just kind of get everything into the type of units that we're going to use to be able to get a milligrams per cubic meter or a ppm. So there are 35.3 cubic feet per cubic meter, so times 1 cubic meter per 35.3 cubic feet. So divide by 35.3, and we're left with 399.4 cubic meters. I just can't keep that paper straight. Alright, so our volume is 399.4 cubic meters, and we're told that our flow rate is 1,000 CFM, which is cubic feet per minute. So we need to go ahead and get that into cubic meters per minute. That would just make things easier. So 1,000 divided by 35.3 is going to be 28.3 cubic meters per minute. Alright, and what we're wanting to know is what will the concentration be after 30 minutes. So the formula that's best for that, I have that pulled up here. Concentration in time is equal to the generation rate, and we'll want to work on our generation rate here in a second, plus it's everything coming into the system, plus the concentration of the outside air, of the makeup air that's coming in, multiplied by the flow rate. In this case, we're going to assume that outside there's not toluene. So we might be bringing in dust and debris or maybe diesel particulates, whatever, because it's coming from the loading dock. But in this case, we're going to assume our concentration is 0 because that's why we're bringing in air in from the outside. Divided by the ventilation rate, Q, And then this is multiplied by a decay constant, e to the minus g times k, minus k q t over v. Make sure that I did that correctly. Yes, e to the minus k q t over v. Okay, so this is our time decay function. So as time gets larger, this goes to 0, which means that this overall expression goes to 1, which means that it doesn't affect the initial expression. So if we simplify this, we say our time, and I said that it was a well-mixed box, so our mixing factor should be 1. If it were a standard industrial setting where there's some ventilation and a mixing factor of around 3 would be more appropriate. Maybe 5 or 10, it just depends. But in this case, we're simplifying it so that the mixing factor is just 1. So we have a generation rate divided by a ventilation rate multiplied by 1 times e to the minus k, which is 1 qt over v. All right. So, let's see. So our generation rate, this is toluene, and the density of toluene is 0.87 grams per mil. So if we just multiply by 0.87 grams per mil, then our generation rate should be, we'll get our generation rate in grams per mil. So 250 times 0.87, and then that, to get into milligrams, we'll just multiply by another 1,000. Something is not doing right here. 250 times 0.87. There we go. And so 21,700 milligrams per hour. And then we want, so I should just do this right here. 250 mils per hour multiplied by 0.87 grams per mil multiplied by 1,000 milligrams per gram multiplied, we want to go from hours to minutes because these are flow rates per minute, and so 1 hour per 60 minutes. So now we're in milligrams per minute. And this might be a kind of atrociously large number, but it's going to make our units cancel and simpler later. So 250 times 0.87 times 1,000 divided by 60. So it's 3,625 milligrams per minute. No, where's my eraser? Alright, so there we have it. So we just plug this in, recognizing that our time here needs to be internally consistent. We could do this all on the hour scale, we could do this on the day scale, we could do it on the second scale. We just have to use our same time constant everywhere. So our generation rate of 3625 milligrams per minute divided by a flow rate of 28.3 cubic meters per minute multiplied by 1 times e to the minus q, which is 28.3 cubic meters per minute multiplied by time, 30 minutes, divide by volume, which is 399.4 cubic meters. So we're left with no dimensions in our exponent, which is good. We don't want to have to try to figure out how to interpret, doing an exponential function on these units. And so 28.3 times 30 divided by 399.4. So this is minus 2.1256. So if we take the E of that, this is 1 minus 0.1193. So this whole expression comes out to 0.8806. So, I mean, thinking about it just more mathematically, you see that we're basically saying whatever the ratio of the generation rate to the ventilation rate multiplied by 0.88, 88% of it is going to be whatever our answer is going to be our concentration at this time. And so when we type this all out, we find out that our C 30-minute equals 112.8 or 113 units are important here, milligrams per cubic meter. Okay, so you can convert that to ppm if you'd like. It doesn't matter, especially right now, unless I ask for it. Let me make sure that I didn't ask for it in specific units. Nah. Okay. And so now, at the steady state, then I ask you, how does this compare to being at the steady state? So this would be part B. And this is really, really simple because C steady state, well, C steady state is equal to the generation rate divided by the ventilation rate. And that's because if we have the 1 minus E to the K Q T over V, as T goes to infinity, this goes to 0, which means that this goes to 1, which means that it's just G times Q. So after a long time, the concentration at steady state is the same as G over Q, generation rate over ventilation rate. So here our C steady state is equal to 3625 milligrams per minute, and that divided by Q, which is 28.3 cubic meters per minute. Our minutes cancel, we're left with milligrams per cubic meter. And that's 3625 divided by 28.3. Oops. So 128.1. So 128 versus 113. So how does it compare? Well, they're pretty close. But as I pointed out, when we were working this out, the 1 minus E to the K Q T over V, G over Q, this expression came out to 0.88. So basically it's 88% of the way to steady state. So just because 88% of the way concentration-wise, that doesn't mean that it's 88% of the way time-wise. This is an asymptotic function, so it will take an infinite amount of time to truly reach steady state concentration. But from an exposure standpoint, when are you going to say, well, that's close enough that we can consider this a standard exposure or a regular exposure, a predicted exposure? So I want you to discuss that and give me your own interpretation and input. So I'm not going to continue discussing that. So this is the end of homework set 7. Hope you've enjoyed it.